Mars, our planetary neighbor. It's very cold and dry, and its weak gravity only holds a thin atmosphere. As probes started to visit the red planet, we gained a more accurate view of the surface, and scientists began to wonder. Mars had once been much warmer. It had rivers, and in its early years might have sustained life. A succession of new techniques have been deployed trying to unlock the secrets of the red planet. And while our knowledge of the Martian geology, its atmosphere, and its weather has grown immensely, each new mission to Mars raises more questions than it answers. We still don't know if Mars has, at some time, been a home to life. In 1877, astronomer Giovanni Schiaparelli made what he thought was the most accurate map of Mars yet drawn. On it, he showed canals. In the early 20th century, American astronomer Percival Lowell was convinced the canals were signs of a civilization existing on the red planet. So began the search for life on Mars. In 1962, the Soviet Union sent the first probe, the Mars M1, on a flyby mission. It was an audacious project, and it failed. The first of many failures by both the Soviet Union and the United States. Cold War rivalry provided the motivation for these early missions. In 1971, NASA sent Mariner 9 to Mars. It was the first probe to orbit another planet, but scientists discovered that Mars was enveloped in a planetary dust storm. On-orbit photography revealed little more than a red cloud. Soon, Mariner 9 was joined by two Soviet orbiters, both equipped with landers. The Mars 2 lander crashed, but the Mars 3 lander made it to the surface intact. It returned one garbled image and then stopped functioning. Mars now had 3 orbiting spacecraft, all looking at a dusty, featureless planet. The two Soviet probes were identical, but the American probe had one key design difference. While the Soviet orbiters began photographing the planet following predetermined schedules, NASA were able to command Mariner 9 to wait, in hope that the dust would eventually settle. It took months for the atmosphere to clear, but when it did, Mariner 9 saw 3 craters protruding above the dust. They were the tops of giant volcanoes on what was called the Tharsis Plateau. Soon more complex geological features began to emerge. In places, the surface was cratered, suggesting the tectonic forces that constantly renew the Earth's surface were absent on Mars. Volcanic activity that built the solar system's largest volcanoes had stopped billions of years ago. This enabled NASA scientists to compile an accurate global map of Mars and to decide upon landing sites for the Viking probes that followed in 1976. Viking 1 and 2 were identical orbiters, with landers that both made successful landings on the surface. Both returned pictures of the Martian landscape. The primary objective of the Viking program was to find signatures of life. But researchers now feel the 3 experiments tasked with carrying out the analysis had limitations. As researchers on Earth began looking for traces of life in extreme environments, they began to rethink where life on Mars might survive. Yet the consensus at the time was that Mars was sterile, and the idea of life on Mars died. After a 20-year hiatus in Mars research, Mars Global Surveyor went into orbit in 1996. The pictures it relayed back were clearer than anything yet seen from the Red Planet. Although most Mars orbiters had been tasked with mapping the planet's surface, this was different. The high-resolution images that the Mars Global Surveyor sent back revealed rivers and even river deltas, but the occasional impact crater suggested that nothing has flowed in these systems for billions of years. In July 1997, another probe arrived. The Mars Pathfinder was one of a new breed of missions being pushed by NASA's new administrator under the guiding philosophy of faster, better, cheaper. The idea was to cut development times, cut budgets, and although the risk of failure would rise, the reduced price tag could mean more missions. Pathfinder would land a small rover on the surface. To do this, it used radically new airbag technology. The technique drew more from automotive safety systems than from previous space missions. The landing site in Mars' northern hemisphere, known as Ares Vallis, is one of the planet's rockiest areas, yet it was thought to be a safe area to land. The broad array of different rock types are believed to have been deposited during an ancient flood. The new landing technique worked perfectly and served as a proof of concept that would be used on future missions. Pathfinder consisted of a base station equipped with 3 solar panels that unfolded like petals. There were sensors to measure atmospheric pressure, air temperature, and wind speed, as well as a transmitter to communicate with Earth. In addition, Pathfinder acted as a base station for the Sojourner rover that explored the surrounding area. Sojourner was fitted with cameras and an alpha particle X-ray spectrometer. It was the first mission to have its own website. The rover returned thousands of images and important detail about the atmosphere and geology, and its popularity guaranteed more Mars missions. On the morning of April 7th, 2001, another Mars orbiter was launched. Mars Odyssey was equipped with 3 primary instruments, and it had the ability to act as a relay satellite between future surface missions to the Red Planet and Earth. On its arrival at Mars, it used a new technique to go into orbit. After firing a relatively brief pulse of its engine, Mars Odyssey went into a highly elliptical orbit that, at its closest approach, had it skimming the planet's thin upper atmosphere. Called aerobraking, this technique allowed the craft to circularize its orbit over a period of 3 months, and it saved around 200 kilograms of fuel. The probe is still in operation today, breaking all records as the longest-serving Mars mission. In December 2003, a new player arrived at Mars. The European Space Agency, using a Russian launcher, had sent Mars Express, its first planetary explorer. It was equipped with a lander known as Beagle. Though all contact was lost with the lander, Mars Express continues to return valuable data. The mission has been granted several extensions, the latest till 2020. Equipped with a high-resolution stereo camera, the probe returned unique 3D views of the planet's surface. The orbiter determined that the polar ice caps contain a blend of frozen CO2 and water ice. In the atmosphere, Mars Express detected first methane and then ammonia. Both gases deteriorate rapidly in sunlight, so there must be sources on Mars continually producing them. Methane and ammonia can rarely be made inorganically, but they're generally associated with life. 1 month after Mars Express went into orbit, a NASA lander arrived at Mars, followed 3 weeks later by a second identical craft. They were the Mars exploration rovers called Spirit and Opportunity. Spirit, the first to land, was targeted at the Gusev crater. Opportunity would land at the Meridiani planum on the opposite side of Mars. Though they were much heavier than their Pathfinder predecessor, they used the same bounce landing technique. Both landings were successful and on target. After the craft had righted itself, it detached from the lander and began autonomously unfolding its solar panels and camera mast. While this was happening, the team back at the Jet Propulsion Laboratory waited. Signals confirming the craft's safe arrival took 15 minutes to travel back to Earth. Many of these people had invested years of their lives in this project, and the real mission had only just commenced. Both rovers were designed to operate for 90 Mars days. A solar day on Mars is about 40 minutes longer than an Earth day. And to avoid confusion, the science team operating the rovers refer to a Martian day as a sol. Mission designers, knowing about the dust storms on Mars, felt that the solar panels on the two rovers would eventually be blocked with dirt and stop functioning. But it became clear that the winds on Mars were clearing the panels. Soon, NASA announced that Opportunity had found evidence confirming liquid water had once flowed on Mars. There were pictures from the Meridiani planum of stratified patterns in the rock suggesting sedimentation. The distribution of chlorine and bromine at the site were clues to the areas past as the shore of a salty sea. In April 2004, NASA announced it would extend the rover's missions from 3 to 8 months. It would be the first of many such mission extensions. The rovers were equipped with an abrasion tool to grind away a portion of a rock's surface for a more detailed, uncontaminated analysis of geological samples. This was first done by Spirit at a rock named Adirondack at Gusev crater. It was a first in planetary geology. Researchers agonized before using the tool because of the drain it makes on the rover's energy budget. The rock was made of olivine, pyroxene, and magnetite, making it very similar to volcanic basalt on Earth. When Spirit's right front wheel stopped working, engineers used a duplicate rover to devise a reversing technique that enabled the rover to drag its frozen wheel. This left a furrow behind in the soil, which presented a new area of research for the science team. White or yellow deposits seen within the furrow were various types of salts that only form in the presence of hot water. On Earth, hot water provides an environment in which microbes can thrive. Spirit limped on for another 3 years before it became stuck in loose sand. Again, the engineers began working with a replica which they placed in an identical situation. When nothing was able to free the rover, it was declared a stationary research platform. Further attempts were made to position the rover so its solar panels could operate more effectively, but even this was not possible. The last communication from Spirit was in March 2010. Opportunity lasted until June 2018, when dust clogged its solar panels. In March 2006, NASA's Mars Reconnaissance Orbiter arrived at Mars and began the now routine business of aerobraking. Though this procedure took roughly 6 months, the saving in fuel will see the craft functioning at Mars into the 2030s. One of the primary functions of the new orbiter is as a communications relay station. Its 3-meter antenna transmitting in the ultra-high frequency band enables very high data rates. By November 2013, it had tripled the amount of data sent to Earth by all the other NASA missions combined. Its high-resolution camera began revealing the surface of Mars in the finest detail. These are active falling dunes in East Coprates Chasma. The polar region, free of the seasonal dry ice, again surrounded by dunes. In the southern hemisphere, pits in the residual cap of carbon dioxide. The poles of Mars were now attracting keen interest. Follow the water had become NASA's catch cry. The Phoenix lander was targeted at the northern polar region to follow up on information from Mars Odyssey suggesting frozen water lay beneath the surface near the poles. Because imaging had revealed the region to be unvarying, a rover was deemed unnecessary. The lander had been designed to use a parachute to decelerate, with rocket thrusters to deliver the craft to the surface, unlike NASA's previous 3 rovers, which had bounced. This decision proved controversial, as one strand of research suggested the rocket fuel would contaminate the very area that the lander was tasked with analyzing. The craft waited 15 minutes to allow any dust to settle before it deployed its solar panels. Phoenix had landed during the early spring in Mars's northern hemisphere, so the solar panels would receive plenty of light for the planned 90-day mission. As well as its camera mast, Phoenix was equipped with a meteorological station that recorded the daily weather. It featured a wind indicator and pressure and temperature sensors. In addition, a vertically pointed LiDAR was able to observe cirrus clouds forming in the region and snow falling in the polar atmosphere. These phenomena had not been observed before. The lander also had a robotic arm that could dig half a meter into the soil and deliver samples to the analyzer, a combination of 8 high-temperature ovens and a mass spectrometer. In one excavation, the cameras recorded a white substance which gradually disappeared. Given the temperatures and the time it lasted, it could only have been water ice that sublimated after it was exposed. The soil was slightly alkaline, and the presence of perchlorate, which kills bacteria, was not good news for those hoping for Martian life. Phoenix operated for 2 months longer than planned before the gathering winter completely shaded its solar panels. While the planet still had subterranean deposits of ice, there was precious little left at the surface, yet it was now understood that many of the red planet's features had been carved by running water. Samples analyzed from across the planet affirmed that water and nothing else had made these changes to the Martian landscape. Mars had once been more like Earth, yet it had lost its surface water and most of its atmosphere. And the question of life persisted. Could it have emerged in a warmer, wetter past? And could it still be present below the surface? The next Mars mission would be NASA's most ambitious yet. Known as Curiosity, the car-sized rover would be powered by a nuclear battery, making it immune to the dust problems experienced by Spirit and Opportunity.
7, 6.
Curiosity was launched on an Atlas V from Cape Canaveral in November 2011.
1. Main engine start, 0, and liftoff.
In mid-2012, it entered the Martian atmosphere heading for Gale Crater. The Jet Propulsion Laboratory monitored the entry closely, but had no control over events. In Mars's thin atmosphere, the parachute could only slow the heavy craft to around 320 kilometers per hour. Nearing the surface, the rover descent stage dropped out of the aeroshell and rockets kicked in. At this stage, radar was guiding the lander to the surface, and a small camera was recording images of the terrain below the rover. Next, Curiosity was lowered on a tether beneath the descent stage. This sky crane technique was used to avoid too much swirling dust exposing the rover to unnecessary danger. Everything had worked exactly as it was supposed to, and the American engineers were relieved. The landing had been the most precise ever. Before Curiosity could start work, its computer went through a checklist to make certain that all systems were operating correctly. It was a day before the rover deployed its camera mast and communications antennas. It's thought that Gale Crater is 3.5 billion years old, and that its sediments have been laid down first by water and then by wind. NASA now has a sophisticated mobile science laboratory on Mars, connected to Earth by the most advanced communications link, courtesy of the Mars Reconnaissance Orbiter. The rover's primary objective is to discover if conditions suitable for life ever existed or still exist on Mars. It's also gathering detailed information about the current conditions on the Red Planet, particularly the radiation levels that will have an impact on proposed manned missions. Curiosity has analyzed the dust from a number of holes it drilled, revealing sulfur, nitrogen, hydrogen, oxygen, phosphorus, and carbon, all elements essential to life. In its 6 years on the surface of Mars, Curiosity has traveled around 20 kilometers, but the driving is taking its toll. It routinely sends back a series of self-portraits, mainly for diagnostic reasons. Its wheels have taken severe damage, which will undoubtedly lead to design changes for future rovers. Its computers are also giving problems, but a new suite of missions is slated to arrive at Mars in 2020 that will continue profiling the planet. There is one aspect of the Martian environment that has never been investigated, but that's about to be addressed. The Mars InSight probe has been targeted at the flat Elysium Planitia, close to the equator, to spend 2 years investigating the planet's interior. It made a flawless landing in November 2018. After unfurling its solar array, it spent weeks selecting a suitable spot to deploy a seismometer onto the surface to monitor Marsquakes. It's clear that Mars had a warm, wet past, but it's cold and very dry now. Learning about the planet's geological activity will help us know why Mars has changed. The InSight probe also hammered a thermal sensor into the surface to gather data on heat flow from the planet's core. By understanding processes within Mars, we can learn how the geological histories of Mars and Earth began to diverge. The ringed planet Saturn. More than 100 times the mass of Earth, its metallic core lies beneath 80,000 kilometers of liquid hydrogen and helium. It's called a gas giant. Saturn is orbited by at least 62 moons, each unique, some with complex and dynamic environments. Our only detailed examination of the Saturnian system ended in 2017, when the Cassini probe was intentionally crashed into the planet's dense atmosphere to guard against accidental contamination of the moons. Viewed from Earth, Saturn's rings are visible, but not in any detail. They were thought to be solid, until mathematical analysis suggested they were orbiting particles. But how did they get there? And why was Saturn alone in having rings? In the early days of space research, Saturn was just too far away. Conventional rockets could only just reach Mars. In 1964, NASA realized that a space probe launched in 1977 could take advantage of a rare alignment of the outer planets to fly past all the gas giants. Using gravitational assistance from the planets, it would just be possible with the technology of the day. An ambitious new mission began to take shape. It was dubbed the Grand Tour. Two probes that were far in advance of anything yet attempted would be part of the Mariner series. Because no spacecraft had been sent beyond Mars, mission planners felt it would be wise to send two rudimentary advanced probes to Jupiter and Saturn to test the deep space environment. Researchers didn't know if it was even possible to cross the asteroid belt between Mars and Jupiter. In 1972, Pioneer 10 was launched towards Jupiter, and the following year, a twin, Pioneer 11, was sent to Saturn. Both craft passed by Jupiter and discovered that the electron radiation there was 10,000 times as strong as at Earth. This was a surprise to engineers at NASA, who had to modify the more sophisticated craft they were preparing for the Grand Tour. The probes, being built at NASA's Jet Propulsion Laboratory, were part of a program known as Mariner Jupiter-Saturn, but this was soon changed to the Voyager program. They were launched 16 days apart in late 1977, while Pioneer 10 was heading toward interstellar space, and Pioneer 11 was still 2 years away from Saturn. In 1979, as Pioneer 11 approached the ringed planet, it began sending back pictures far clearer than anything seen before. A new ring, the F ring, was observed for the first time. The craft flew by Saturn, passing beneath the rings. Mission planners were uncertain how broadly the ring particles spread. If there was a threat to the spacecraft, they were prepared to sacrifice Pioneer 11 to get a clear idea of the environment they would encounter with the following Voyager craft. The probe passed the rings safely and continued beyond Saturn into interstellar space. NASA received its last communication from the probe on the 24th of November 1995. The following Voyager I and II probes were very robust, designed to survive for a very long journey and with far greater technical capacity than the Pioneers. In late 1980, Voyager I approached Saturn. Although its high-resolution polarimeter had failed, it was still able to see a new ring called the G ring, orbiting 100,000 kilometers above Saturn's cloud tops. For the first time, researchers could see how the rings moved. Uneven features within the rings were called spokes. They're transient and are thought to be particles lifted by an electrostatic charge. After such a long preparation, information was now coming into JPL at such a rapid rate that the planetary scientists were overwhelmed. Saturn's moons were of great interest. Voyager I's path had been chosen because it would take it close to Titan, the solar system's second largest moon, and the only one to hold an atmosphere. But the images were disappointing because the thick atmosphere of methane and nitrogen was impenetrable. Voyager I now looped up above the solar system on a trajectory that would take it to interstellar space. As it looked back at Saturn, it captured one last image from a unique angle. It was almost 10 months before Voyager II neared Saturn. Its different path meant that it could continue on to Uranus and then to Neptune. Its high-definition camera was still working, and planetary researchers were expecting detailed pictures of the rings. They were not disappointed. The varying densities and spacing within the rings was more complex than anyone had expected. The rings are named for letters of the alphabet in the order that they were discovered. It became apparent that the rings had changed in the time since Voyager I had seen them. Though they stretch from 7,000 to 80,000 kilometers above Saturn's equator, their thickness is on average just 30 meters. The spacecraft also returned pictures of the moon Enceladus. Its cracked, uncratered surface was made of ice, below which is an ocean. Ultimately, Voyager II left Saturn. Unable to go into orbit, it sped on toward Uranus. It would be 23 years before another probe visited.
And liftoff of the Cassini spacecraft on a 30-mile trek to Saturn.
Launched in 1997, Cassini was a collaboration between NASA, the European Space Agency, and the Italian Space Agency. It would take more than 6 years to reach Saturn. Cassini was the biggest, most complex interplanetary spacecraft yet devised. Its 12 different instruments each had a dedicated team of research specialists on Earth to interpret the data it sent back. Its high-gain antenna was used for high-speed data relay back to Earth, but in what's called a ram maneuver, it was sometimes used as a shield to protect the spacecraft from debris impact, especially when crossing the plane of Saturn's rings. On the 1st of July 2004, it fired its engine to go into orbit around Saturn. It was designed not to fail. Beside its main engine was a backup in case the primary engine did fail. It had 16 monopropellant thrusters, 8 prime, and 8 more, also as backups. In mission control at the Jet Propulsion Laboratory, the engineers could not know what was going on. The time delay and Cassini's disappearance behind Saturn meant that much of the telemetry was recorded for later replay back to Earth. The engine burn lasted for 106 minutes. Cassini was the first probe to employ a solid-state recorder, unlike the earlier Voyager craft that registered data on a mechanical tape recorder. Cassini's first orbit followed a highly elliptical path that would take it out past the moon Titan. This was important for two reasons. Its gravity would be necessary in modifying Cassini's course, so Saturn and its other moons could be observed from different perspectives. Secondly, Titan, with its dense atmosphere, was targeted as an area of major interest for the Cassini team. The European Space Agency had built a small craft called Huygens, attached to the side of Cassini. On its second approach to Titan, the Huygens probe was released. It was equipped with a heat shield, a parachute, and enough battery power to last for several weeks. Over a 20-day period, Huygens drifted for 4 million kilometers. It would transmit data back to the orbiting Cassini, which would later relay it to Earth. 3 days after separation, Cassini made a course correction that would prevent it colliding with Titan. As Huygens reached Titan's atmosphere, Cassini was coming around for its third close approach of the moon, ready to receive signals from the lander. While it drifted to the surface of Titan, Huygens sampled the atmosphere and recorded images of the landscape. Pictures from beneath the clouds revealed low hills and channels cut by flowing liquid. There were few impact craters, and those that existed were heavily eroded. It was the first landing on a body in the outer solar system. Images from the surface showed weathered rocks made of water ice. What surprised everybody was that Titan is a geologically active world, where liquid ethane and methane, rather than water, have carved the features. As Cassini continued looping out around Titan, it used radar to map the moon's surface, confirming the widespread distribution of hydrocarbon lakes. The probe discovered that rain fell on Titan, but it was a mixture of liquid ethane and methane. The moon has weather and other erosive forces similar to Earth, but the chemistry is radically different. The small moon Enceladus drew attention to itself as the whitest, most reflective body in the solar system. Its surface shows cratering in the north, but the south has giant cracks known as tiger stripes. On Cassini's first loop past Enceladus, the magnetometer team noticed an odd deflection of Saturn's magnetic field, as though the small moon had an atmosphere. During its second pass, the team noticed the same phenomenon. They asked for the next traverse of Enceladus to pass much closer, so Cassini's course was modified to fly just 175 kilometers above the icy moon. The probe passed through a plume of water vapor emanating from the tiger stripes. It contained common salt. In all, Cassini made 24 swoops past Enceladus, with the closest approach flying just 25 kilometers above the surface. Each one of the probe's instruments gathered different evidence about the jets of water expelled through the cracks in the moon's south. On Mars, rovers have been combing the surface looking for traces of life. but Enceladus was flaunting remarkable signs. Gravitational analysis revealed a liquid ocean beneath the ice, and infrared detectors saw heat emanating from the cracks. As well as salt, the science team discovered traces of silica that can only dissolve in hot water. Hydrogen and organic compounds were also detected.
We know from Cassini that Enceladus has a global ocean, so you have water. We also know that there are organics coming out because they've been directly measured, both in the gas and in the particles. We also know there's a source of energy. The South Pole was hotter than the rest of Enceladus. And then we found evidence that deep inside, there are hydrothermal vents on the seafloor of Enceladus. So these hydrothermal vents would supply the heat and the nutrients that could possibly support life.
With a diameter of 500 kilometers, Enceladus is just too small to sustain a hot core via radioactive decay. Gravitational squeezing by Saturn explains some of the heating, but the source of the high temperatures detected remains a mystery.
But not only is there liquid water underneath the surface, but there's organic material, there's a heat source. And you know, when people get excited about the potential for life elsewhere in the solar system, there are four things that you need. You need a heat source, you need liquid water, you need organic material, and you need those three things to be stable over some period of time so that life could potentially form. At Enceladus, we've got three. We're not sure about the stability over time yet.
In the Earth's deep oceans, hydrothermal vents provide the warmth and nutrition to support life. They may even have been important for the origins of life. Planetary biologists are speculating that the environment in the oceans of Enceladus may be the most likely place in the solar system to find some sort of extraterrestrial life. It took a while for Cassini to be in a position where backlighting from the sun allowed the imaging team to capture pictures of the plumes. Using a similar technique, the imaging team took this picture with Saturn directly between Cassini and the Sun. It reveals Saturn's E-ring, the hazy outermost ring that is usually very difficult to see. The E-ring is a result of the plumes from Enceladus and is constantly replenished by the saltwater eruptions. Saying that Saturn has 62 moons is misleading. Each particle within the ring system could be regarded as a moon. There are the inner large moons and the outer large moons. There are the shepherds that shape the rings. There are co-orbitals that exchange orbits. And there are even moons that orbit other moons. All are unique. During the Voyager missions, interest in the moons came as something of an afterthought. But for Cassini, close examination of the moons was planned from the beginning. Iapetus orbits Saturn beyond Titan. It was first observed in 1671 by Giovanni Cassini. He could see it as a dot of light to the west of Saturn, but could not see it when it should have been to the east. Iapetus has one bright face and one dark one. Because the moon is tidally locked to Saturn, it is always the dark face that leads as it orbits. One theory suggests that it sweeps up debris that spews from Phoebe, a more distant moon. Another feature of Iapetus has scientists baffled. A ridge along the equator stretches more than halfway around the moon. It's twice as high as Earth's tallest mountain. With Iapetus being just 1,500 kilometers across, the ridge gives Iapetus the appearance of a walnut. Very accurately directed bursts from Cassini's main engine allowed mission engineers to modify the probe's looping orbits so mission specialists could focus on various moons, different areas of the ring system, or different parts of Saturn itself. With gravitational assistance from the moons, particularly Titan, mission control were able to conserve fuel. The Cassini probe performed so well it received 2 mission extensions, but the fuel could not last forever. Planners had scheduled the most hazardous part of Cassini's mission for its final year at Saturn. Late in 2016, Cassini began a series of polar orbits that would take it close to the outer edge of the rings. In what mission specialists called grazing on the rings, the craft's mass spectrometer and its cosmic dust analyzer would sample particles and gases as it crossed the ring plane. In orbit 251, its first pass above Saturn's North Pole, it recorded the peculiar hexagonal storm that was first hinted at by the Voyagers. The storm, more than twice the diameter of Earth, maintains its hexagonal shape, but its color changed with the advance of summer. At its center is a cyclone, shown here in false color, with red indicating lower cloud and green higher cloud. Winds at its edge blow at 540 kilometers per hour. One part of Cassini's dual-technique magnetometer had stopped working early in the mission. Without it, the craft had to do roll maneuvers from time to time to calibrate the instrument. The spacecraft would make 20 ring-grazing orbits, with the work of its instruments mapped out to the second. As the Sun was almost directly behind the rings, Cassini looked for dust clouds. Something is reducing ring particles to fine powder. Cassini made a number of radio occultation observations. With the rings between the spacecraft and Earth, 3 radio signals of differing wavelengths were transmitted simultaneously, allowing the radio science team to build a profile of the ring particles. This false color image of the A ring, the outermost of the large bright rings, shows red for particles larger than 5 centimeters across. Green denotes particles smaller than 5 centimeters, with blue for particles smaller than 1 centimeter. The complex gravitational interaction between Saturn, its rings, and its moons leads to gaps in very particular places. Before Cassini arrived, only 18 moons were known. That number has grown to 62. Prometheus acts as a shepherding moon, limiting the inner edge of Saturn's F ring. Along with Pandora, which orbits outside the F ring, the 2 moons keep the ring narrowly confined. In April 2017, Cassini's orbit was changed for the final phase of its mission. The probe would now loop inside the rings. Though it would ultimately mean burning up in Saturn's atmosphere, the information gathered from such close proximity to Saturn and its rings would give a fuller picture of the gas giant. It was decided that intentionally destroying Cassini was preferable to letting it drift without fuel, possibly contaminating one of the moons. Cassini's sensors began picking up a stream of ring particles raining down upon Saturn. A continuous shower of ice and dust particles are dragged toward the planet's equator by gravity, or at higher latitudes, charged ring particles spiral in along magnetic field lines. Every second, 10,000 kilograms of ring rain falls to the surface. At this rate, the rings will be completely gone in 100 million years. Researchers were surprised to discover an electric current flowing between the inner D ring and the upper atmosphere. Toward the end of Cassini's close passes of Saturn, the spacecraft began catching the upper edge of the atmosphere. Vital information had been retrieved from the recorders. Data now was transmitted directly back to Earth, but it relied on the spacecraft's thrusters to stop Cassini from tumbling, keeping its high-gain antenna pointed accurately. The probe's final work was sampling the atmosphere and measuring the offset of Saturn's magnetic axis.
This is ACS-1. We just had transition to high rate mode.
In mission control, there was no more control. The engineers could just monitor the signals sent from Saturn 84 minutes previously.
The signal from the spacecraft is gone, and within the next 45 seconds, so will be the spacecraft.
It will take years to process the data gained from Cassini. As yet, there are no future missions to Saturn scheduled.